Record. Okay, so Compton scattering is a third phenomenon besides photoelectric effect and black body radiation. And this phenomenon also shows that particles, I mean, light behaves like particles. And essentially, what you have to know about this is that you have a light particle, a photon. We can draw it like a particle, but it's also a wave. So some modern understanding of light particles is that they are packages, waves, or wave packages. Let me just make it a little bit better. So, so I'm trying to use my iPad to draw this. I don't know if it's going to go better or not. Like that. It's not better. I don't know. So let's see. We're gonna destroy this thing. All right. So that's a photon. That's a photon. Photon. And it collides with an electron. Now, electrons are not like free electrons. You have to understand that electrons would scatter photons, but it's more interesting to shoot photons at the atoms and see what's going to happen. So if you have an atom, then you may have, so we have an atom here. So you may have elastic collision, where basically photons will be scattered off the atoms. You may have no collision, which means you will have a transparent medium, and you may have inelastic collision. So that will create absorption of the energy, and it will excite electrons. So let's actually write it down. So 3 types of interaction between photons and atoms. So 1, photons pass through without interaction. There may be some interaction. There may be absorption, re-emission, or photons will go through this electromagnetic field inside the medium. It will slow them down. So we have refraction phenomena explained by that. But even if you have refraction, that's a transparent medium. So we can say that it means that we have transparent medium. Medium is transparent. Okay, number 2, we have elastic collisions. And these collisions will happen with specific kind of atoms, I mean photons, and this creates opacity. So it will allow the light go through, but at the same time, light doesn't go through without any collisions, and these collisions create, elastic collisions create scattering effect. So scattering light of the atoms, molecules maybe, depends on the size, molecules. And this material then will be opaque. So medium is opaque. Like that, or maybe translucent. Okay, so and the third one is going to be inelastic collisions. Inelastic collisions. So in this case, we can have either complete absorption, right? So complete absorption. And in this case, we have like a black body object that absorbs all the kind of energy, all kinds of photons. And the object will be looking dark or black, right? The complete absorption depends on which colors, again, it's absorbing, or partial absorption. Absorption. So when you have partial absorption, and that also refers to like a particular color may be absorbed, right? I think we talked about leaves. They're green because they absorb the red part of the spectrum, and they reflect the green part of the spectrum. So Compton scattering is an example of inelastic collisions of photons, primarily X-rays, with inner electrons. So we can write it down. So Compton scattering is interaction, inelastic collision, inelastic of X-rays. So we need to have high energy photons, otherwise nothing will happen. Inelastic collision of X-ray photons. Photons with the inner electrons of the atoms. Okay, so whenever this happens, you have a specific kind of spectrum. So the light will be absorbed only within particular narrow range, right? So for this, we have the formula that looks like this. Let me see if we can do that. So light looks like this. So we have lambda, the wavelength, the final wavelength, minus the initial wavelength, which we will call delta lambda. And that's equal to Planck's constant, mass of an electron. We're talking about electron scattering, so it specifically applies to electrons. 1 minus cosine theta. So what's happening here is you have a photon. Again, let's try to draw it. A photon flying forward to the right. And suppose we have an electron here. And what happens is then the electron will be deflected like so, right? So we'll gain certain kinetic energy. The photon will lose energy, and if it loses energy, it has to have a longer wavelength. So energy of a photon is expressed as HF, or we can write it HC over lambda, right? So if energy becomes lower, the wavelength has to become longer. So this wavelength will be initial wavelength, shorter wavelength. This will be representing longer wavelength, final wavelength. And the only thing you should remember, like for at least for region purposes, is that Compton scattering is an example or a phenomenon where photons behave like particles. And if you look at the equation, H is Planck's constant there. So it will, photons will lose energy only in certain amounts, certain quanta. Okay, so that's basically it about Compton scattering. Why is Compton scattering important, or how is it useful? If you scatter light of electrons, you can actually kind of scan the inner structure of atoms, and this is how all those SPDF levels, especially inner electron levels, have been pictured. So this way you can actually create a picture, a three-dimensional picture of electron clouds inside the atoms. And all those connections between like hybridization of electron orbitals, they all come from Compton scattering experiments. Okay, resume recording. So how do we understand amplitude of the waves? So basically, this is what we have. When you have a single photon, its energy is represented by HF. If you have more than one photon of the same kind, then you have, in this case, 3 photons. Obviously, we'll have 3 HF. In this case, 3 is just a number. It doesn't affect the frequency. Each of them has the same frequency. So if I were to represent this as a wave, this wave would be looking like this, right? This wave will be looking like this. So basically what we have here is amplitude of the wave here. So let's put it amplitude is A. This amplitude will be well, it won't be 3A, it will be root 3A, because energy is proportional to the amplitude squared, so I have to put the square root of 3A. In a very simple interpretation, you can say it's 3A, so you just don't bother about actual quantitative relationship. So the number of photons is represented as the amplitude of the wave. Now, if you have two kinds of photons, one is going to be like that, high frequency, and that is going to be low frequency, then obviously we'll have two kinds of waves. So they're basically already here, but I'm going to draw that anyways. So this will represent this wave, and this will represent, this will represent high frequency wave, this will represent low frequency wave. Right, now what do we have? Lots of these guys. So, and then this will be represented as high frequency and also high amplitude wave. Now, what do we have? 3 of the photons of low frequency. Like that, right? So this will then be represented by a wave, which has, again, high amplitude, but low frequency. Okay, so that's how you can understand the relationship between two models representing the same thing, the light phenomenon, right? Photons, the energy depends on the frequency. Energy of the wave depends on the amplitude. Energy of the wave also depends on the frequency, but then you have to go back to the photons. So in the last two examples here, the wave, this wave will have higher frequency, thus it will carry more energy than the wave with lower frequency. So this wave carries lower frequency, so less low energy. By amplitude, they will be the same. Okay, so this is like how you should understand the photons and waves. Any other questions? All right, so if you don't have any questions, so what we have here is a representation of photons or light in the form of photons and the form of waves. So how can I understand amplitude versus photons? So let's say we have a single photon, its energy is equal to HF, right? And if I represent this as a wave, this will be like a wave of certain amplitude A. Now let's say we're shooting 3 photons at the same time, going in the same direction. So energy will obviously be 3 times as much. It doesn't mean the frequency will be 3 times as much, but it means that the amplitude of the wave will be greater. Now, mathematically, it should be √3 times A, because intensity or energy of the wave is proportional to A squared. So you have to put √3 rather than just 3 here for the amplitude. But like you can forget about this and just say, well, the amplitude will be greater by a certain quantity, right? And that represents that we're shooting more than a single photon or more light. So brighter light means higher amplitude. Don't confuse brighter light with our color perception, because you perceive certain colors better than other colors. Yellow, green range, we're more sensitive to that. We can actually, see it better. Can't see violet as much. So even if you have really bright violet light, our eyes and brain will interpret that as a rather dim source of light. While yellow and green light may have little energy, but since we're sensitive to that, our response will be, oh, that's a very bright source of light. So this is about the same frequency, but different amplitudes. Here we have a photon of higher frequency, higher energy. So we can represent it as a wave of higher frequency. So if you want to make it more intense, more energy, you have to shoot more photons, which means the wave will be represented with a higher amplitude, but the same frequency as this wave, right? Essentially. Now, if we have a photon which has lower frequency, right? This will be representing that wave. If we want to make that light brighter, but again, not how we perceive it, brighter in terms of amount of energy, then we're going to send more photons, which will be represented by the wave of greater amplitude. So this way you can make a connection between energy, wave interpretation of light, and particle interpretation of light. So particle wave duality was the next logical step. So at the turn of century, in 19th to 20th century, right, we have a few things going on. We have photoelectric effect, we had black body radiation, which was successfully explained by Planck. Photoelectric effect was explained by Einstein. Einstein also came up with E equals mc squared equation, which is coming from special relativity theory. And it came to the point that people started accepting that light could be both wave and a particle. And another development helped kind of solidify this. So a French scientist, a young scientist, he was actually just a few years younger than Einstein. a French royal, so he is a prince. He was a prince rather. So instead of like dedicating his life to whatever, he decided he's going to become a cool physicist. His name is Louis de Broglie, and that's how I think you pronounce de Broglie. And basically, he hypothesized that, well, if light can have energy and momentum, which was proven again by Planck and Einstein, then particles can also have obviously have energy and momentum. Equivalence of energy and mass was proven by Einstein. Then why particles, regular particles, cannot, behave like waves? So his hypothesis was that a regular particle, and at that time there wasn't a lot known about particles except electrons and maybe protons, the nucleus, right? Or atoms, right? So why can't they behave like waves? So what you see here is not really derivation, but it's a kind of conceptual approach to figuring out relationship between the mass energy and wave energy. So E equals mc squared is actually delta E equals delta mc squared. It's part of the formula that Einstein came up with. So we're going to use just that E equals mc squared part. So energy that is confined within a certain amount of mass will be mc squared. We hypothesize that this mass could be turned into a wave, so it will behave like a wave. So then its corresponding energy will be hf. We can also write hf as h times c over lambda. So lambda represents the wavelength. So then we can simplify this expression as mc equals h over lambda. And then finally, we can solve it for the lambda. And here we do a little abracadabra, hocus pocus, and we just replace c, which is speed of light, with v, which is the speed of a particle. So this particle will be, say, a particle, an electron. So this will correspond to the mass of an electron. It could be the mass of a proton. It could be the mass of the entire atom. It could be the mass of a piece of rock. I don't know, a rocket. Doesn't matter what it is. So the point here is that anything that has rest mass, which is you can put it on a scale of sorts and then weigh it, so it's not moving constantly, it's not going at the speed of light, that is called rest mass. So objects that have rest mass cannot move at a speed equal to the speed of light. Okay, and so they will move at speed less than speed of light. That's why we label it as v. For the photon, this equation boils down to simple like energy. If you look E equals hf, right? You just find lambda from there. So lambda will be equal to hc divided by the energy of the light of the photon. So it's more important for particles. Okay, so in a way, you can think that any particle of any mass could behave like a wave. The question is it really practical to consider that? And since Planck's constant is rather small, it makes sense to consider that only tiny particles with tiny mass moving relatively slowly will exhibit wave characteristics, which can then be detected. So de Broglie gets the Nobel Prize for his work, and another gentleman, Thomson, last name Thomson, and he was, I forgot, George Thomson, I think his last name is Thomson, definitely, the son of J.J. Thomson, right, who discovered electrons. Electrons were particles. So his son, after about 30 years, discovered that electrons can actually behave like waves. So he was scattering electrons off the crystals and discovered that they create a diffraction pattern, which means they are behaving like waves. Okay, and that earned him a Nobel Prize as well. So let's calculate the wavelength. So let's see, we can calculate the wavelength of an electron. So we have mass of electron is equal to 9.11 10 to the negative 31 kilograms. Suppose this electron is moving relatively slowly, so 100,000 meters per second. That's pretty slow for an electron. So we need to find the wavelength. Okay, estimate the wavelength and then put in the chat box. Okay, so basically what we established is that if the electrons move slower, they interact with the larger objects, right? I mean, I don't know, you may consider like a long molecule. You want to scan that carefully, and you can shoot electrons at that. And then the pattern may create, the pattern that's created may then give you an idea like the dimensions of the molecule, if it's like a long biological kind of molecule or like polymer kind of molecule. If you want to see what's going on with the crystalline structure, you will shoot the high-speed electrons that will scatter and create diffraction pattern based on which you can figure out the structure of the crystal. Again, this could be used for forensics. For example, you can study materials, you can study forgery, you can study crystals. You can have, like, let's say you got a mix of sand and you want to study what's inside there. You can find composition of the sand, like it will be made of like a certain number of atoms of particular kind, or you can have crystals of quartz plus crystals of calcite plus crystals of topaz or whatever. And then you can also have a composition like in terms of percentage of each crystal within the mixture. So it has lots of applications. Now there's another application which is really interesting, and it's kind of sci-fi. Technologically, we have lots of challenges, but theoretically, there's no really, there's no, the answer is not no. I mean, yes, we can actually do that theoretically, but technologically, we're not there yet. So what I'm talking about is that all of you probably familiar with Star Trek, when they beam people from place to place for fast travel. And so the idea of beaming came from, again, Einstein's idea equals mc squared. The mass is converted to the energy of in form of light. This idea was used, for example, by Herbert Wells in the War of the Worlds, lasers, right? Martians were shooting lasers, laser guns, right? There was a Russian science fiction, well, Russian writer, and he wrote a few science fiction novels, even though he was not like a science fiction writer, like merely focusing on science fiction. Last name Tolstoy, not related to Leo Tolstoy. So he wrote a novel about an engineer who came up with this invention, a laser, and he was a crooked man. He decided to conquer the world using his lasers. And Isaac Asimov came up with a short story in the 1930s. I think the story was called something like a human being as a beam of light. There must be my more poetic title. So a beam that can be like human can turn to beam of light. So basically, a man would travel between the planets and stars, and he would be turned to beam of light. And while traveling, he would not experience any aging, obviously, because light doesn't age. There's no notion of time for light. So again, technologically, there's no really, I mean, theoretically, there's no problems. The problem is technological, right? And then we can even just look at this and say, okay, what if we turn a human being? It doesn't have to be a human being. It could be like a payload. Let's say I want to send like a, I don't know, payload to Mars, right? 100 kilos. So if we use same formula, we quickly realize that the Planck's constant is too small, right? Here we have V, so V has to be virtually 0 for this wavelength to be substantially longer or long enough so we can actually handle it and send it in some direction. So we have two issues here. One is that V has to be approaching 0. And 100 kilograms is lots of particles. You want to make sure each particle slows down to almost 0 meters per second, right? Which translates to 0 Kelvin temperature. Now it has been done, this has been done. People were able to cool a small collection of atoms. It depends how you treat it, small, large, thousands of atoms, to temperatures really close to 0, 10 to the negative 9 Kelvin, I think. So this temperature, they behave collectively as one object, actually. And it hasn't been done, like they did not shoot it as a wave, because the moment you give them energy, the temperature increases and all of a sudden this breaks apart. So it's a technological rather than theoretical problem, because part of this has been solved, bringing temperature to 0 Kelvin, close to 0 Kelvin. The second step is shooting this wave through the distance and then catching it. So all these are technological problems rather than theoretical problems, mainly, right? And obviously, with a human being, you can't freeze a human being to 0 Kelvin and expect that survive the temperature. So, but 0 Kelvin doesn't mean the object is at 0 Kelvin. It just means the relative speed of those particles is 0. And if you're shooting something over a certain distance, you do it only temporarily. And this, if it's done briefly, right? So it'll be like you close your eyes, you open your eyes, you're on Mars. Okay, you don't feel any discomfort whatsoever. So theoretically, it's possible. Technologically, we're not there. Okay. So that's like a practical application, but it's like a science fiction at this moment. Any questions? We're gonna wrap it up. No questions. All right then. If there are no questions, let me see. Hold on a second. Yep, we have like 3 minutes left. I think we can close the shop. So no questions. I'll see you guys tomorrow. I already posted the assignment on Google Classroom for the homework. 2 questions, 2 calculations. Submit them online. See y'all tomorrow. Bye. 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 Take care. Oh, you guys are awake. Oh my. Have a good day. See ya. Bye. Bye. Okay. Don't forget to sign out. Sign out. Sign out. Wake up. Sign out. MD, are you still there?